The first thing that you will be learning how to do and practicing today is setting up the knowns and unknowns for a projectile motion or two-dimensional motion problem. It's the same as the way we set up knowns and unknowns for one-dimensional motion problems, except we separate our components so we have information in the x direction and in the y direction. For example, for this projectile, shot at 10 meters per second at an angle of 30 degrees above the horizontal, there's an x and a y component of the initial velocity. You learned how to find x and y components in the video that you watched Tuesday or Wednesday night. If the hypotenuse is my initial velocity, then the y component of my hypotenuse, of my initial velocity, is the hypotenuse times sine theta. That's because sine theta is opposite over hypotenuse. So this y component, v naught y, is hypotenuse times sine theta. And you can see that work down here. The y component of my initial velocity is 5 meters per second, 10 sine theta, and it's positive. My x component can be found because cosine theta is adjacent over hypotenuse. So my adjacent side of this triangle, v naught x, is my hypotenuse times cosine theta. And so you're going to use this technique to find the different components of initial velocity every time. 10 cosine 30 gives me 8.7 meters per second, and that's to the right, so it's positive. So I don't just have v naught equals, I have v naught in the x direction and v naught in the y direction. And this may remind you of how in those equations on your blue piece of paper, there's little x's. For example, we have v final x equals v naught x plus axt. That's telling you that this equation works in the x direction and it works in the y direction. We could easily just change these little letters to y's. And you have to treat them separately if you're moving in more than one direction, like in projectile motion. Next, we find the components of acceleration. In the x direction, there is no acceleration. The only acceleration for something in free fall comes from gravity, and that points down, which is in the y direction. So that's why this a sub x is 0 meters per second squared, and a sub y points down, that's why it's negative, and it's the acceleration of gravity 10 meters per second squared. In this problem, our displacement in the x direction is given to us. It's 50 meters, but we're not told the height of this cliff, and that's our displacement in the y direction. Just as a side note, if you're falling down, this is usually negative, especially if you made this acceleration of gravity negative. Time has no dimension, so whatever we find as time on one side of this table is the same as what we find for time on this other side of the table. And it hasn't told us in this picture how much time the object was in the air, so that's also an unknown. We know from physics laws about projectile motion that velocity in the x direction is constant. So my final velocity in the x direction is the same as my initial velocity in the x direction. It's 8.7 meters per second. But velocity in the y direction does change. And it changes because of gravity. That is why we don't actually know this final velocity in the y direction. And so everything that we have a question mark next to, we could use our kinematics equations to find. We're not doing that yet. You'll start doing that probably on Monday. When objects move down ramps, because we already know that they're going to be constrained to moving along this one line, it helps us to make that one line either the x or y direction when we find components. So we do this kind of funny thing and we tilt our x and y axes. So normally this is our y direction and this is our x direction, and we just tilt this axis so that now x is along the ramp and y is perpendicular to the ramp. And as long as x and y are perpendicular to each other, this makes sense. So now we know that there is an initial velocity down the ramp, and I decided to make that positive x, which is no problem. And so our initial velocity in the x direction is 6 meters per second squared, and none of that velocity is into the ramp this way. It actually can't move into the ramp's in the way. So our initial velocity in the y direction is 0. In the x direction, our acceleration is the part of gravity that pushes the box down the ramp. So this is the part of gravity pushing or pulling down the ramp. So some of that gravity is pulling the object into the ramp, and the ramp is pushing back, and some of that gravity is making the object slide down the ramp. But it's not all of gravity, so we need to find that component. So what we do is we make a right triangle, but it's not the same right triangle as is in this diagram to begin with. Because we want to find the component of gravity, which points down, gravity becomes the hypotenuse of our triangle. And we draw a right triangle around it. We can do it on that side, or we could do it on this side, to figure out what the x and y components are. So if this here is 30 degrees, this here is 60 degrees. It's 30, 60, 90. And I redrew it down here so that you can see each side of the triangle with that 60-degree angle. So if I'm finding the component of gravity that is in the x direction, I'm talking about this side of the triangle, it is adjacent to this 60-degree angle, and that's why I use cosine. So a sub x is 10 cosine 60. That gives me 5 meters per second down the ramp, and I decided to make down the ramp positive. In the y direction, there is a component of gravity pushing the object into the ramp. However, the ramp pushes back up. This is called normal force, but all you need to know for now is that when an object's on a surface, the part of gravity pushing it into the surface is counteracted by another force. That's how we know that this acceleration in the y direction is 0. We also know that it's not going to speed up or slow down going that way or that way. So we can logic our way to understanding this. If I know the height of this ramp, that's not really helpful to me because it's neither in the x or the y direction. So I need to figure out what part of that height is motion in the x direction, which basically just means I'm finding this side of the triangle, this red side here. So if this is 30 degrees, this is opposite of my angle, opposite over hypotenuse is going to be sine 30 degrees. So 3 over delta x equals sine 30. You can see that math here. And I rearrange this and I get delta x equals 6 meters. So that's how far down the ramp I would move. I know that in the y direction, I don't have any motion, but something that could be asked of me is what my final velocity is down the ramp, or what my speed is at the bottom of the ramp, and the time it takes to get to the bottom. So those are my unknowns. As a reminder, I figure out my knowns and unknowns partly by listing in my mind all the possible knowns and unknowns for kinematics. So that's initial velocity, final velocity, displacement, time, acceleration. And that's it. So we know our initial velocity in both directions. We don't know our final velocity in the x direction, but we do know it in the y direction. We know our displacement in the x direction. And we don't really need our displacement in the y direction, but we don't have time, and we do know acceleration in the x direction and in the y direction. You are going to use the next 10 minutes to solve the following situations by drawing the appropriate table. So just like I did for you for example 1 and 2, you are figuring out your knowns and unknowns in the x and y direction. So take 10 minutes to do that. We will check it together on Monday, and after you're done with that, you will start the next video.